Good morning to all of you. In previous sessions, we discussed the inverse Z transform by power series expansion, that is long division method. Before that, we have seen the Cauchy residue theorem, that is inverse Z transform by the contour integral. In today's session, we will be discussing inverse Z transform by partial fraction expansion. Right. As we already seen, the inverse Z transform can be identified by using direct evaluation by contour integration. We've seen this one also, that is inverse Z transform by using power series expansion of long division method. And today we will be discussing the inverse Z transform by partial fraction expansion, which is also referred as the table lookup method. Okay. So in case of inverse Z transform by partial fraction expansion, after obtaining the partial fraction expansion, if x of z is any one of these forms, then its inverse Z transform will be represented as, just for example, in the first case, if x of z is in this form, that is 1 upon 1 minus pk z inverse. So here this pk is nothing but the whole value, you can consider it as. So if your x of z is in this form, after applying the partial fraction expansion, if x of z is in this form, that is 1 upon 1 minus pk z inverse, then its inverse Z transform will be simply any one of these, that is pk raised to the power n into u of n, or it can be minus pk raised to the power n into u of minus n minus 1, okay, depending on the ROC condition. Okay. So this particular x of z, after applying the partial fraction expansion, if we get x of z in this form, then its inverse Z transform can be pk raised to the power n u of n, or minus pk raised to the power n u of minus n minus 1. So this inverse Z transform will be there if ROC mod z is greater than this value, that is mod pk, right? So that means it is exterior to circle, that is it is a causal signal, right? And this will be inverse Z transform if ROC mod z is less than mod pk, right? So this ROC is interior to circle, so this will be in case of anti-causal signal. Okay. So this is what we get after partial fraction expansion, right? The another one is if we get the terms in the form, that is pk z inverse full upon 1 minus pk z inverse whole square, right? If we get this term after applying partial fraction expansion to x of z, then its inverse Z transform can be simply n into pk raised to the power n to u of n. Okay, and this will be applicable if ROC mod z is greater than mod pk. Okay. Similarly, there is one more form after applying the partial fraction expansion. If you are getting the values in this form, that is ak, so it may be any constant. So ak 1 minus pk z inverse plus ak, it has multiple forms, ak star, right? There will be multiple terms. So 1 minus pk star z inverse, right? So if you get the x of z in this form after partial fraction expansion, then it will have the z transform 2 mod ak into e raised to power n cos beta k n plus alpha k into rho of n, right? So in this case again, if ROC mod z is greater than mod pk, and this mod pk is nothing but simply the value rk, right? So in most of the cases when we apply the partial fraction expansion, we get the x of z in this particular form, or probably in this form, right? But most of the time this form we will get after applying the partial fraction to x of z, right? So let's see one example how we can write or utilize these uh, forms of x of z to get the inverse z transform by using partial fraction expansion, right? So here is the example. As you can see there, we have to again determine the inverse z transform. That means you have to determine x of n from capital X of z. So x of z is given as the rational function 1 upon 1 minus 1.5 z inverse plus 0.5 z to the power minus 2. There are three conditions of ROC. So in first condition, ROC mod z greater than 1. Second, ROC mod z less than 0.5, right? As you can see that ROC mod z greater than and less than, these two conditions are there, right? And in third condition, in first case ROC mod z is greater than 0.5 but it is less than 1, okay? So both these conditions can be utilized if we are getting x of z in this form after applying the partial fraction expansion. So let's try to solve this example. So here the given x of z is, so it is given in the rational form, that is numerator and denominator terms are there. So it is given as 1 upon 1 minus 1.5 z inverse plus 0.5 z to the power minus 2, right? So here we will try to eliminate the negative powers of z, right? So eliminate the negative powers of z, okay? So to get the roots of this denominator, we are trying to eliminate the negative powers of z, right? So here in numerator and denominator you can multiply with z square, or you can say that you are taking z to the power minus 2 common from the denominator. So if you take z to the power minus 2 common from the denominator, so in denominator you will get z square minus 1.5 z plus 0.5. So that z to the power minus 2 you can send in the numerator, so it will be z square, okay? Or you can say that we are multiplying in numerator and denominator by z square, okay? And the same thing, right? So I'll directly write down here the x of z, okay? So after making that adjustment by taking z to the power minus 2 common from the denominator, so what I will get, so it will be simply z to the power minus 2 in bracket z square minus 1.5 z plus 0.5. I will send z to the power minus 2 in numerator, so it will be z square. So I will get simply z square whole upon z square minus 1.5 z plus 0.5, okay? of this z square, one side I will send on the right hand side. The purpose of this adjustment is that once we apply the partial fraction expansion to these terms, after this there should be again, as you can see in this partial fraction form, there should be z inverse, okay, in the denominator. Okay. So for that purpose we have sent one z on the left hand side. So remaining term will be z upon z square minus 1.5 z plus 0.5. Correct. So once you identify the roots of this denominator, so you will get this as x of z upon z is equals to z upon so it has two roots. So first one is 1 and second one is 0.5, right? So you get this. So if I'm multiplying this minus 1 with minus 0.5, so I'll get 0.5, right? And if I'm adding these two values, that is minus 1 and minus 0.5, so I will get minus 1.5, right? So these two roots are there. If you are multiplying these two brackets, so you will get this denominator term, right? That is z square minus 1.5 z plus 0.5, right? So as you can see here, there are two poles, right? So first pole will be at z is equals to 1. So if I'm substituting z is equals to 1, so 1 minus 1 will be 0 here, right? So 0 multiplied by this term will be 0 and 1 upon 0 will be infinity. Okay, so for z is equals to 1, I am getting value as infinity. Similarly, if I am substituting z is equals to 0.5, so 0.5 minus 0.5 will be 0 again. Another pole will be at 0.5, right? So as per partial fraction expansion, I can simply represent it as a upon z minus 1 plus b upon z minus 0.5, right? So here, if I am sending these terms on the right hand side, so simply z is equals to what you will get, z is equals to a multiplied by z minus 0.5, right, plus b into z minus 1, right? If I'm sending these two terms on the right hand side, so this z minus 1 will get cancelled, a multiplied by z minus 0.5 will be there, plus so b, this z minus 0.5 z minus 0.5 will get cancelled, so z minus 1 will be there, right? So to get the values of a and b, right, if we set z is equals to 1, right, so you will get the value of a, right? If you set z is equals to 1, so 1 minus 1 will be 0, this term will be 0, okay? We get value of a. So how it will be identified? So if I'm substituting z is equals to 1, so this 1 minus 1 will be 0, this complete term will be 0, so it will be 1 is equals to a in bracket 1 minus 0.5, right? So simply a will be equals to 1 minus 0.5 will be 0.5, right? So here I will be sending it to this 0.5 I will send on the left hand side, so 1 upon 0.5 will be equals to 2, right? So the value of a will be 2, right? Similarly here you can set z is equals to 0.5, so this will be 0, you will get value of b, right? So again, if we set z is equals to 0.5, the value of b, right? So here again I'll be writing 0.5, 0.5 is equals to, so this 0.5 minus 0.5 will be 0, this term will be 0, b into 0.5 minus 1 will be there, right? So this 0.5 minus 1 will be minus 0.5, right? So this minus 0.5 and this 0.5. If I'm sending minus 0.5 on left hand side, so 0.5 upon minus 0.5, so 0.5 will get cancelled, so it will be minus 1. So you will get the value of b is equals to minus 1 simple, right? So we have now the values of a and b. You can substitute these values in this equation, right? So now we have this x of z upon z is equals to the value of a is 2, right? So it will be 2 upon z minus 1. So I can write here 2 upon z minus 1, right? And value of b is minus 1. So I can write minus 1 upon z minus 0.5. So that is the term that we have obtained after the partial fraction expansion. Now you can set this z on right hand side. Okay, so what you will get? So x of z is equals to 2z upon z minus 1 minus z upon z minus 0.5, right? So it will be simply x of z is equals to, I can send this z and denominator, so it will be z inverse. So z inverse multiplied by z will be 1, and 1 multiplied by z inverse will be z inverse. So it will be 1 minus z inverse, and here it will be 1 minus 0.5 z inverse. Okay, so I will write down the x of z as 1 minus z inverse minus 1 upon 1 minus 0.5 z inverse. Okay, so this is the obtained x of z after applying the partial fraction expansion. Now we want to identify the inverse z transform of it, right? So for finding the inverse z transform, as we have these three conditions on ROC, right? So I'll rewrite this x of z here initially. So what we have after partial fraction expansion is 2 upon 1 minus z inverse, right, minus 1 upon 1 minus 0.5 z inverse. Okay, so the inverse z transform can be obtained by applying. So if you compare these two terms with what we are seeing, these three forms, right? So these these two terms are in the form simply 1 upon 1 minus pk z inverse, right? In place of pk, the values are 1 and 0.5, right? So we have to apply this form, that is z inverse 1 upon 1 minus pk z inverse, right? So it will have any one of these forms, it is pk raised to the power n u of n or minus pk raised to the power n u of minus n minus 1. Okay, so this will be applicable if ROC mod z greater than pk, and this will be applicable if ROC mod z less than pk. So we have been provided with three conditions in the example. First condition, ROC mod z is greater than 1. Okay, so as per the first condition, ROC mod z greater than 1, right? The signal is causal, right? So if you apply any one of this form, so here you can see that for the given x of z, for the obtained x of z after partial fraction expansion, there are two poles. Okay, so you can say that it has two poles at z is equals to 1 and z equals to 0.5, right? And as per the given condition, mod z is greater than 1, that means it is greater than first pole value as well as second pole value. Okay, so it is greater than 0.5 as well as greater than 1. So therefore you can apply this first form. Okay, so as per this first form, your x of n will be pk z inverse. So in this case the value of pole is 1. Okay, so it will be 1 to the power n. Okay, so this 2 is constant, so 2 will be as it is. Here the first pole value is 1, so it will be 1 to the power n into u of n, right? So into u of n will be there, right? And minus, so here the pole value is 0.5, so it will be 0.5 raised to the power n into again u of n, correct? So here you can simply write it down as x of n. So you can substitute any value of n, so it will be 1 only, right? So it will be simply 2 minus 0.5 raised to the power n into u of n, right? So that will be the required inverse transform as per the first condition, correct? Now the second condition. What is the second condition given here? So it is ROC mod z less than 5. So ROC mod z is less than 5. So the signal is anti-causal, right? So here you can write the x of n is mod z less than 0.5. So x of n will be equals to, so it is less than 0.5, that means it is less than 1 as well as less than 0.5, right? So in both cases this second form will be applicable, right? So you can write, so this 2 will be as it is, right? So minus sign will be there here, right? So because it is minus 1 to the power n, so minus 2 1 to the power n u of minus n minus 1 will be there, right? And again this will be minus, but again here you have to take minus pk raised to the power, so minus minus plus will be there, right? So 0.5 raised to the power n u of minus n minus 1 will be there, right? So again here you can take u of minus n minus 1 common, so here it will be x of n will be equals to minus 2 plus 0.5 raised to the power n into u of minus n minus 1. Okay, so this will be the required inverse Z transform for these two conditions, right? Mod z greater than 1, mod z less than 0.5. The third condition on ROC is 0.5 less than mod z less than 1, right? So before that I will write down this x of z here. So write that x of z, what is x of z after partial fraction exponential 2 upon 1 minus z inverse minus 1 upon 1 minus 0.5 z inverse. Okay, the third condition, ROC 0.5 less than mod z less than 1. Okay, 0.5 less than mod z less than 1. So here you can see the pole value is 1. So here the ROC is less than 1, right? So if it is less than 1, so for this first term this second form will be applicable, while for this second term as z is greater than 0.5, so here the pole value is 0.5, so for this term this first form will be applicable. Okay, so as per that form when we'll apply it, right? So x of n, as it is a two-sided signal, right? So x of n will be simply, so you will get again minus 2, right? As per this equation it will be minus 1 to the power n minus 2 into 1 to the power n into u of minus n minus 1 will be this, right? As per this form. And minus, for this term you will be applying the first condition, okay, because ROC mod z is greater than 0.5 here, right? So as per that condition, it will be 0.5 raised to power n u of n, okay, so it will be 0.5 raised to power n u of n will be there, right? So as per the first term it is anti-causal, as for second term it is causal, right? So this will be the required inverse Z transform for this third condition, right? So this is how you'll be obtaining the inverse Z transform by using the partial fraction expansion, okay. So here we have identified for three different ROC conditions, right? In the first condition, the ROC was exterior, so it was a causal signal. In second condition, it was interior, so it was anti-causal. And in third condition, it was a ring, okay, so it will be a two-sided signal, right? So while for obtaining the inverse transform by partial fraction expansion, initially you will be obtaining partial fraction expansion of the given x of z, and depending on which form you will be obtained, depending on that obtained x of z form, you will be applying any one of these rules, okay, depending on the ROC conditions, right? So here x of z was given, so we eliminated the negative power of z, and after that we identified roots of it, okay. And then as per partial fraction expansion, we obtain the values of these constants. By substituting these constants, we get x of z upon z, right? And to get the negative power again, so we have sent this z on the right hand side. This adjustment has been made for that purpose only, okay. We are saying this z, one z from here on left hand side, x of z upon z we have written. The purpose of that, we need the negative power of z, so that z now here transferred after partial fraction expansion, so it will be z in the numerator that has been sent to the denominator to get the negative power, okay. So if you compare this partial fraction expansion, this was in this form, so therefore this first rule has been applied here, right? And according to that, depending on the ROC condition, we have written the inverse transform x of n of the given x of z. So in next session we'll be discussing some more problems on this partial fraction expansion, okay? Thank you for joining this session.